Okay, I'm just going to do a brief little look at trig functions and how they show us something about oscillations. What do we know about oscillations, eh? Oscillations moving from side to side. There's a midpoint, there's a point in the middle, and the object is going the same amount to both sides of that middle point. There's a minimum and a maximum, and the speed of the object that's oscillating, the speed at either end of the oscillation, at the minimum and the maximum, or the left and the right, okay? Or the top and the bottom, the speed when you get to either of the two end plates, if you like, is going to be 0, right? So left and right, imagine a grandfather clock, yeah? So you can imagine that on a grandfather clock, the pendulum is swinging from the left to the right, from the left to the right, and when the grandfather clock pendulum is right as far to the left as it's ever going to be, for a split moment, there is no speed on the pendulum, and then the speed starts to go the other way. Let's have a think of top and bottom oscillations. Do you remember those old computer ping pong games? Yeah, this sort of thing, where you've got a little, well, these are from left to right, so that doesn't help me, but some of them were up and down as well. But it's that kind of an idea, isn't it? Up and down on like one of those old computer ping pong games or something like that. That kind of oscillation. Right. So, you know, we'll put in there computer ping pong or something like that. What's the case of a minimum and a maximum oscillation? Well, something like the tide, because if the tide in a beach, the minimum point at which the tide occurs might be here on the beach, right? And obviously the beach will be zigzaggy, so this will just be some point, and here's our sea. And then at a later date, the sea will come in more, and will be up here, right? So all of these cases, the thing needs time to slow down, come to a standstill, and then start moving in the opposite direction. So the tide is moving at its fastest right in the middle between high tide and low tide, right at this point here. That is the fastest that the tide is coming in or going out, because right at the end, at the furthest reaches of the tide is coming to a standstill. It was rising and rising, but it's just come to a stop, and it's about to start receding and going down. And in that moment, when it's at its furthest reach of the tide is neither going in or coming out for just a second. It is just at a standstill, because it was going in one direction and now it's starting to come the other way. This is at the heart of simple harmonic motion, and it is at the heart of the trig function, which describes, I say that the trig function is at the heart of sine and cosine trig functions which describe that simple harmonic motion. It's not like the tan graph, but yes, sine and cosine are effectively the same function moved along, left or right. So if I have the sine function here, and you'll have to forgive me because I'm not using the grids, so the period is probably out a bit, but that's roughly what a sine function looks like, right? And I could have a cosine function and it will look a bit like this, and they're just phase different. They're just the same graph moved left or right of a sine function. So I'm going to get rid of all of that and start again. Let's have a look at some things on this graph because they can be really handy. Okay. First thing to talk about is the gradient, okay? Because in simple harmonic motions, we're going to look at the gradient, and to look at the gradient, we're going to need to have a look at the x-axis and what the x-axis represents. And the x-axis is going to represent time. That's really important. It's going to represent time. As time progresses, this motion is going to occur. Now, we are used to, in our most basic understanding of trigonometry, functions that have a +1 and a -1 as their minimum and maximum. So if we're looking at the sine function, we'll look at something like this. And it doesn't go above 1 or -1. We can do things to the function to change it, and we will very shortly. Let's call that f of x equals sine x, where x in some ways is talking about time. Now, I want to talk about the gradient. The gradient is how quickly this quantity, which for now we'll just call this meters, right? Distance, because this is the easiest thing to think of when we're thinking of simple harmonic motion. Whether it's a pendulum and how far it's moving, whether it's a Ferris wheel, whether it's the ping pong game, or whether it's the tide. Let's think about it in terms of meters for now. And with that in mind, let us look at the gradient, because the gradient is telling us how the distance traveled is changing with regard to time. So at this point here, the gradient dy dx is 0. That means that the object was rising to +1 meter. Let's imagine that it's the level of the tide, but instead of looking at it looking down on the beach, let's imagine that we're looking at the beach like a cross section, right? So this is the beach going down, this is the sea at high tide, at low tide, and then this is the level of the sea at high tide. Okay. And we'll call this the midpoint. Okay. So at high tide, and at the moment we're saying that high tide is 1 meter above the midpoint, at that point the tide is neither coming in or going out. It's come to an absolute standstill. And now if we look at the gradient here or here, the gradient is very steep downwards, negative, so the tide is going out, and it's going out at its quickest at that point there, the midpoint. And here the tide is coming back up again, and it's going up at its fastest right at the midpoint. So that is just a little bit of understanding to do with the gradient and how that helps us understand simple harmonic motion. If we've got meters or centimeters or millimeters on our y-axis, our dy dx is going to be meters or centimeters or millimeters per second. It's going to be the speed of the thing. And as we've talked about with a grandfather clock or with the tides, the speed is going to be highest right in the middle of the oscillation and lowest, 0 in fact, right at the far ends of the oscillation, because it's just slowed down to stop to start going the other way, and for that split second it's 0. And the split seconds that the gradient dy dx is 0 are the moments that we've come to the end. One final thing to look at, we will have to have a look at some point at how we can make these trig functions work for us in a given scenario to do with time. But for now, I'm just going to have a look at how we can make these scenarios work for us in terms of distance. So if I have a look here, quite briefly, I could make my high tide and my low tide 10 meters apart. Okay, it's unlikely, but let's say it's 10 meters apart. So if I was going to do that, I would want my top point to be, well, it's going to be 5 meters from the midpoint, and my bottom part to be 5 meters from the midpoint. So I'm going to want a function which goes up and down (5 meters), because that reflects a tide which has an overall difference of 10 meters. 5 meters above the midpoint line, 5 meters below the midpoint line. Now, how can I get my function to do that? Well, this bit is really easy. So I've got my 5 meters here, I've got my negative 5 meters here. I'm going to take this function, the sine function that I had, and that sine function was giving me 1 and negative 1 at the maximum points. So I'm going to take every value the sine function comes up with, and I am going to multiply it by 5. Okay? And I've now created a sine function that sketches out for me the undulation, the oscillation of the sea in a tide where the high tide and low tide difference is 10 meters. Next time, we're going to have to look at moving trig functions to the left or the right to mimic what we're trying to look at in certain situations. And we're going to need to look at stretching or compressing our sine function so that we can take account of, you know, the time between high tide and low tide is going to be quite different than the time between the highest point of my grandfather clock's pendulum and the lowest point. That's going to take, my grandfather clock's pendulum is going to take a few seconds to go from the top to the lowest point. The tide is going to take hours. So how can we stretch or compress our sine functions to reflect the different things that we're modeling? We'll have a look at that next time.